Good morning, everybody. This is Jay Foley from Foley Lab. I'm going to talk to you a little bit about our WPTherml software package today. If you've already been to our Willie P. Chem YouTube page, you might have seen that we already did a demo on radiative cooling. I thought today it might be appropriate to just take a step back and talk a little bit about the software package in general and how it works and what we intend it to be used for. So in a nutshell, WPTherml is meant to be a software design engine for materials for harnessing heat. Okay, and so the idea then is that what you can do is if you have applications in mind that depend on the optical properties or the thermal radiative properties of materials, then you can investigate those materials. You can screen them for their potential usefulness for these applications. You can optimize them or design them, and you can use our software package to generate insights that can help push your research and those kinds of applications forward. That's the vision. How does it work? So right now, underlying WPTherml is a rigorous electrodynamics engine called the transfer matrix method. And you may know something about this method if you're interested in material science or optics or physics or chemistry, and you may not, which is fine. There's actually a lot of information on our documentation about it. But one shortcoming, one limitation of this method is that it is useful only for materials which are flat. Okay, so basically multi-layer stacks of planar structures is what we can currently support. Will we support other kinds of materials, other kinds of geometries in the future? Absolutely. Right now, though, it basically materials which vary only in one dimension. Nevertheless, there's a tremendous variety of materials and interesting optical and thermal radiative properties that can be realized by just multi-layer stacks of thin films. Okay, actually there's whole textbooks written about them. They're actually really amazing structures. If you don't know about multi-layer thin films, check them out. They're pretty cool. Now why do we actually care about thermal radiation? Okay, so handful of reasons why. Tremendous amount of the energy that we produce in the United States and actually globally as well is wasted as heat. Okay, there's a tremendous amount of thermal energy coming down onto Earth from the sun spectrum. And we actually use quite a bit of energy dealing with heat, doing things like air conditioning and that sort of thing. So the ability to harness heat, the ability to convert, reclaim, and convert heat and waste heat, and the ability to more intelligently dissipate heat are all opportunities that exist within the renewable energy and energy efficiency space. So tremendous opportunities out there to design and engineer materials that can help with all of those applications. And there's not really a lot of open source tools available to design those sorts of materials. So we want to help fill that need. And we also hope that will inspire people to think creatively about these kinds of challenges and opportunities. Okay, so just the only slide I'll show with equations in it, how this whole thing works is that when you talk about how a material loses energy as heat, specifically through radiation, and you may remember way back to your sort of like first time you ever took physical science, there's like 3 ways that you can lose heat, right? You can exchange heat through conduction, convection, and radiation. And so in our software package, we're only concerned about the radiation part. How do materials absorb or lose or exchange heat through radiation? So through the way that they do that is through thermal absorption and thermal emission. Okay, and thermal emission is sort of like the principal quantity that we compute, and it can be defined as the product of 2 different spectral quantities. And by spectral, I mean that depend on wavelength. The first quantity is called Planck's black body spectrum. So this derives from something called Planck's law. okay? And this is a universal piece of thermal radiation. The other piece is the part that we can control, which is called the emissivity, okay? And the emissivity we can control in a number of ways. One is through the kinds of materials that we use. So what are the actual identities of the materials? Are we using things like tungsten, like metals, tungsten, titanium, steel, iron, gold, whatever? Are we using materials like glass, aluminum dioxide, or aluminum oxide, titanium dioxide, that materials that are transparent? Are we using semiconductors like silicon, germanium, that sort of thing? Okay, all of those different materials have different sort of fundamental emissivity properties, but also actually how we structure them. If we make them into thin films, if we stack those films, that will change their emissivity properties. If we did other things, which we can hopefully deal with in the future with our package, like pattern them on the surface, cutting grooves into them, making pyramidal patterns and so on. There's all sorts of things people do in nanoscience to impart additional structure to these materials that will also change emissivity. So we have a lot of ways that we can manipulate this piece, and then this black body spectrum is basically universal, just depends basically on the temperature. Okay. So, that engine that I mentioned underlying WPTherml is all about actually computing this emissivity spectrum. And it does so basically by computing first the reflectivity and the transmissivity of light through whatever multi-layer structure you define. And from those two quantities, actually the emissivity and the absorptivity are inferred. Okay, and this is a rigorous technique, but again, it works for multi-layered nanostructures. Okay, so that's a little bit of the motivation about our software package. Let me now hopefully open up. Here we go. Our web page. So there's quite a bit of documentation already on our web page about how to use it, what kinds of features are supported, syntax that you need to know. So I encourage you to go here. If you care about the mathematical details of the underlying transfer matrix engine, plus how we relate those outputs to the different kinds of figures of merit for different applications that you can investigate, those details are given also in our documentation, linked to from the web page. I want to try to quickly go through a couple of examples that just demonstrate a few of the basic capabilities of WPTherml. So these are examples that actually will ship with our software package. So as soon as you clone WPTherml, you're going to have these examples on your computer. And so if you have Anaconda Python installed, you will have Jupyter Notebook and Jupyter Lab. So you can open up these Jupyter Notebooks and go ahead and interact with them. Okay, and so I'm just going to really quickly take you through these. So example 1 actually doesn't deal with thermal properties at all. It just deals with optical properties, like basically reflectance and transmission and absorption of a glass slab. Okay, and actually further on down the line, there's gold slab as well. So importantly, every time you want to use WPTherml, the first thing that you need to do is actually define some structure that you want to characterize. And we tried to make that as easy as possible. So you have to define the materials. There's keywords for a whole list of materials that you can consider. Here we're considering a glass slab. So basically the keyword for glass is SiO2. And you need to also tell us the thicknesses or the geometries of those materials. So everything is a planar structure. So really the only dimension that you can specify is the thickness of those planar materials. So thickness list will specify the thickness of each layer that you have. Okay, lambda list, this is basically the array. This defines the starting and ending wavelength over which you'll characterize the material. So we're going to get basically the visible spectrum of this glass slab. Okay, and the multi-layer class will get this dictionary as an argument. So this is a dictionary which contains features of the structure you're trying to model. You're going to pass that dictionary to our multi-layer class, and then that's going to create an instance of your object, which in this case we're calling glass slab, and that will be then that instance will have associated with it different properties that you can investigate, either by printing those properties out or by plotting them. So in this case, we'll plot the reflectivity, transmissivity, and emissivity of that glass slab, and this is what we see. In blue is transmissivity, so the glass slab is very transmissive. Most of the light goes through. It's fairly reflective at certain colors, and it is not absorbing at all, which was basically consistent with what we know about glass. This is another little method associated with the multilayer class called ambient color. And so what you can do is you can say, okay, well, my material reflects these colors of light, 400 to about 550. It's very, very non-reflecting here. Reflects these colors of light here. Okay, so what will it actually look like to the human eye? That's what ambient color does, is it actually creates a rendering of this reflectance spectrum as a visible color. Okay, if I wanted to do something like change the thickness, I can go in and change one of the attributes of glass slab, which is D. That's the thickness. D element 1 is the thickness of layer 1. There's only one layer in this multi-layer. That's layer 1. And then we can go ahead and re-update all of the optical properties by using this method called Fresnel, and run that again. We'll get new spectra. And since there's new reflectance spectrum of that thinner slab, we've gone from 200 nanometers to 50 nanometers, it should be a different ambient color. And we can run the ambient color method again and see that it's changed. Okay, so that's optical properties only. If you look at example 2, you can actually see some thermal properties come into play. This is actually looking at incandescent bulbs. These are like the old school light bulbs that are getting phased out because they're not so efficient. This actually will do a few things. So what we can do is we can compute, we can make our instance of our multi-layer object called W slab in this case. Notice we did a couple of things different. Number one, we set the temperature to be very hot. These incandescent bulbs are very hot. They're close to 3000 Kelvin. Number two, we used a different material. In this case, we used tungsten. And that's actually because the material used to make incandescent light bulb filaments is tungsten. I made it a little bit thicker. It's actually probably way too thin for a real tungsten filament, but that's okay. Lambda list, we went between the visible and now the mid IR. And then we also turned on this flag called light bulb. Okay, and I'll show you what that does. So as soon as we create this class, in fact, when we use the light bulb library, it's actually going to immediately plot two spectra. One is the thermal emission spectrum of our structure. The other is the black body spectrum. So you can see that the black body spectrum is well above the thermal emission spectrum of our tungsten bulb at basically all colors. Okay, but nevertheless, tungsten bulb has a very broad thermal emission spectrum, right? One thing to point out is that you can really only see this region of the spectrum right around here, somewhere between 400 and 800 nanometers. So really you wouldn't like for your tungsten bulb to be emitting in the IR, but it is. We can characterize this quantity called the luminous efficiency. This actually takes the fraction of the thermal emission spectrum which is actually visible to you and divides it by the total thermal emissions, thermally emitted power, and turns that into a percentage. And you can see that this is basically about 5.5% efficient, which is not so good. It means about 95% of the power is wasted as heat. So that's not so great. Okay. One other thing that we can do is when we have a structure which is 3000 Kelvin instead of 300 Kelvin like at room temperature, most of its appearance actually derives from its thermal emission, not its reflection. So we can actually render that thermal radiation spectrum as a color again and plot it, and that's what the method thermal color does. So you can see that here. So that's just a short demonstration of a few of the different capabilities that exist. If there are other capabilities that you would like to see added, you can comment in this YouTube page. You can contact us through our GitHub page. If you're interested in being a developer for WPTherml, you can contact me with any ideas that you have for possible extensions and collaborations. I'd love to hear them. I hope you enjoyed this short demonstration, and I hope you have a great time using our software package to do exciting science. All right, talk to you soon.